guys, I miss you, and I'm gonna look at the first 6 chapters of those cumulative review exercises today. It shouldn't take that long. It should be a pretty quick video. Chapters 1 through 6, it's pretty repetitive. They have you looking at summary stats over and over again, so a lot of it will go pretty quick. I already have them done here, so I'm just gonna be looking through and making sure that you understand the problems. The next few chapters, I'll probably group them in how they're grouped per week. Like I'll do maybe 7 and 8 together, and then maybe 9, 10, and 11 together, maybe 2 videos instead of 1, because those ones are a little bit meatier chapters. So let's go ahead and look at chapter 1. All right, make sure its focus is on it. There we go. So for chapter 1, the first thing that they want us to do is find the mean. This chapter in particular, there's not really a lot of actual math that goes on here. It's more just you're playing with the calculator. Can you actually calculate the numbers? So they give you these, and they even tell you, can you add it up and divide by how many there are? So you end up with 3,162.5 grams. And then it asks you note anything about the measurements. Well, they all end in zeros, so they were probably measured to the nearest 100 grams. That would be my guess. The next one, you're just playing with your calculator. Same thing, here you're finding a z-score. We have a z-score of 16, which is very abnormally high, right? That's a very significant value. We don't expect to have a z-score of 16. We don't expect z-scores over 3, so a z-score of 16 is wowzers high. The next one, you're finding another z-score. This one is a z-score of negative 6.64. That one's abnormally low. They didn't ask us that in this one because, remember, we're just dealing with can you play with the calculator for chapter 1. That's all that they were looking at. Most of these calculations, if you remember things as you go, then you might recognize them. This is a z-score using the central limit theorem, right? Because I've got my my standard deviation divided by the square root of my sample size, so I'm using my central limit theorem to find a z-score for this one. The next one is actually finding a sample size, right? If we have our margin of error, which in this case is 3%, then this is how we would find our sample size, and we'll look at that again in chapter 7. The next one says the range rule of thumb. Bring water bottle here. Use that, or the range rule of thumb, to find an approximation for the standard deviation. So the range divided by 4, you get 575 grams. The next one, once again, you're just plugging it in. Same thing. All of these, you're just plugging it in. And then these, they wanted you to recognize, hey, pay attention to your calculator. I want you to pay attention to these because if you get a probability of something like this, I still have people telling me that you have a probability of like 6.6. You can't have a probability higher than 1, remember? So pay attention to when your calculator is giving you that E, right? So that was pretty much it for chapter 1. Chapter 1 was very short, very sweet, just looking at can you use your calculator for the most part. Chapter 2 started to get into a little bit more of the math that we've done. It looks at can you make a frequency table? And if we look here, or frequency distribution, oh, I'm wobbling everything. I'm all wobbly. Okay, so this one here, I've got all of my data right here, and so they want us to construct a frequency distribution. They tell us to use a class width of 5 and a starting time of 235. So I started off right here with 235 and then 239, right? Because I go up by, if my class width is 5, that's the distance between my 2 starting values, right? It's always, or my 2 ending values. There's a difference of 5 there. So I have 235 to 239, 240 to 244, and so on. My frequency, I just go through and I just count them up. Just tally them up. You end up with 439,833. Okay? It asks for just looking at the first class. What are the class limits? The class limits are the numbers that are listed there. What are the class boundaries? Well, that's going to be what would come right before this and what's in between here, right? If I was on a number line, then these are the numbers that would be in between, kind of sandwiching in my class. So it's 234.5 and 239.5 are going to be my class boundaries. The class midpoint, it's just the middle way between those two numbers. So just add them up, divide by 2, and you get 237. Next, they want you to take this and turn it into a histogram. which is pretty easy to do. These become your numbers along the bottom, right? I just listed all of my starting values for each class. And then I used my frequencies to create my bars. Pretty easy. Remember, with a histogram, your bars should be touching, right? There shouldn't be any space in between them. Number 4, it asks, let me read it here. Assume that you want to create a histogram for exercise 3 in a way that exaggerates the difference among the times. That would be by starting it like right here. If we were to have our x-axis start right here, so not start at 0, but instead start at maybe 2, or heck, maybe even start at 3, right? That would really exaggerate the difference between my upper and my lower times. The next one is a stem plot, and we did a little bit of stem plots, but not a whole lot. So looking at this stem plot is a good quick review. You did these way back in like 6th, 7th, 8th grade, a little bit this year, but we haven't really looked at them that much. So if I want to look at my stem plot, I look at here and I have numbers that start with 230s, 240s, 250s, 260s. And so that's what my 2-3 stands for, is 230. So this is 236, 237, 238, 239, and so on. And so you just go through your data and mark it up. And if I'm looking at this, right, if I turn it sideways, it looks to be approximately normal, right? It looks as though it starts off low, gets high in the middle, and then gets low again. It's pretty symmetrical, so it could be approximately normal. Okay, so that was chapter 2. Ooh, that was super crooked, sorry. Chapter 2, cumulative exercises. All right, let's look at number 3. Number 3, I'm not going to go into a lot of detail with these first ones because they are exactly the same, except for they don't want us to look at class widths or anything like that. They just want us to look at those frequencies and then make a histogram for it, make a stem plot. This one's a little bit different because I don't have hundreds and tens values over here. Instead, this is my ones value, and then this is my decimal point, right? So this one right here is 1.5. This is 4.9. This is 5.4, 5.4, 6.1, 6.3, 6.6, 6.7, 6.9, and so on. Number 4, put my sticky note on the wrong page. Sorry. There it is. Number 4 is using that same set of data, getting those descriptive statistics. So all I did was I just put it into my calculator and hit that 1 var stats, right? It's just stats over to calculate and then go, right? So I've got my x bar, which is my mean. My sample mean is 6.09. My median, 6.45. My standard deviation is 1.75. Variance, I meant to have you skip this one, but I didn't put that down. Anytime that we come across variance, remember, we didn't really look at variance a whole lot, so anytime that it shows up, we just skip it. But remember, variance, it's really simple. It's just the standard deviation squared. So the standard deviation squared is 3.06 if you did that one. And then the range is just your upper minus your lower, so you get 6.7. And then number 5, that one is really easy. I'm going to put this here so we can see it together. Eek. There we go. What's wrong with this graph? Right? If I'm looking at this, it does not start at 0. Okay? I'm going to go ahead and, oh, I didn't do number 6. Okay, well, let's do number 6 together right now. It says, examine the distribution shown in the histogram from exercise 5. Why does it appear the sample comes from a population with a normal distribution? So let's look at that graph one more time. Does this appear to be normal? And as I look at this, remember that normal distribution is that bell-shaped curve. It should start low, get high in the middle, come back down, and it should be symmetrical. This is not symmetrical in any way. It doesn't start low, get high, get low again. It definitely does not appear to be normal. So I would say that not normal, it's not symmetrical, or bell-shaped. Remember, for a normal distribution, that's what we're looking for, is that bell-shaped curve. I don't know why I skipped number 6, but we did it now, right? Okay. The next one, chapter 4. And I'm sure you guys saw chapter 4 and got all freaked out because you're like, oh no, it's probability. But remember, these are the cumulative review exercises. So there is probability there, but it's not like the entire section is probability. In fact, it starts off with another data set, that's one thing I liked about these, was they give you a lot of data sets to work with, so you can continue to practice getting your summary statistics. One that I probably should have had you skip because we didn't really talk about it too much, but it's not hard to find, is the mid-range, and that's just the average between your max and your min. So you just are finding the middle of your range, and so that ends up being 0.220 for this one. But all of these, you can find them the same way that we did before. Number 2, they want you to get your 5-number summary. So remember, this is your min, this is Q1, this is your median, this is Q3, and then this is your max. And then they want us to make a box plot. 0.35 does appear to be an outlier. It is pretty darn high out there. The next value would actually be right here. So if we wanted to make this a modified box plot, we would have it end there. And if you graph that on your calculator and did that modified box plot option, it probably would have looked like this, right? We can modify that box plot to have our outlier be poking out there. And then C was another, why are those all weird? There we go. C was another stem plot, but in this case, where we've got even smaller values, so we've got 0.0. In this case, the stem here is going to be made up of the 10th place, and then all of these are the 100th place. That's all that a stem plot does, is you have one spot where you're saying, okay, this is the place value that I'm starting at, and then these are where all of my data stem off of it. Okay. Number 3 was they were looking at a sample, and they had how many internet users are willing to donate organs after death, and they wanted to know what percentage that was. Well, this many said that they would, and that was 46%. What is the probability of one person randomly selected from the survey that would donate their organs? And that is 0.46. Remember, probabilities, we tend to give them as decimals and not percents, but if you said 46%, remember they're kind of interchangeable, so we aren't too nitpicky on that. What kind of sampling method was it? And they go, in the beginning, they describe that in this sample, or in this survey, 100 adults were surveyed in each state and the District of Columbia, and results were weighted to account for the different state population sizes. So in that case, what you're looking at is a stratified sample, right? They're trying to make sure that each different state, or in this case, District of Columbia too, everything is accounted for appropriately, right? So that means California was accounted more heavily than other states. So it was stratified. That's where you break it up. A lot of you were looking at that with your projects, breaking it up into freshman, sophomore, junior, senior, right? And collecting surveys from each of those different groups so that you would have enough. That's stratified sampling. Number 4 is eye color. And this is where we start to get into some stats, right? So there was a professor that said eye colors are distributed like this, and so the stats instructor collected eye color data from her students. That's a convenience sample, right? And then identify one factor that might make the sample biased, and that would be that a college class doesn't necessarily represent all of the population, right? When you're looking at college, and even with something like eye color, you might think that because we're dealing with eye color, that distribution might not change because you're not dealing with age or income levels or anything like that. However, you are looking at ethnicity. Ethnicity can be a huge factor with eye color. And so a college class is not representative of all Americans, since they may be disproportionate with regards to ethnic groups based on location. Different ethnic groups might choose to go to different colleges, and colleges in general, especially nowadays, can actually be much more diverse than some areas of our country are in general. So that would make it not representative of just America. So we would want to not just look at one college class to try to make a actual sample. Letter C says the probability of brown or blue. Oh, did I not finish this one either? Oh my gosh. I'm Okay, I'm gonna have to finish this one with you. This is gonna be a longer video. That's a bummer. So brown or blue, that's where we take the probability of brown plus the probability of blue. We add them together and we get 75% or 0.75. Part D, I used binomial. We didn't have to. You could do a lot of different things with this one, but I used binomial just because it was the easiest way to do this one. And so we're selecting two people. We know the probability of having brown eyes is 0.4. And so I want to know what is the probability that at least one of them has brown eyes, right? So that means one or two people are going to have brown eyes. So I want the complement. I want to find this probability right here. So binomial PDF of 2.4 and then 0, because remember this is n, p, and x. And I want to go 1 minus that because I want this probability, not that probability. So I plugged this in, I got 0.36, so 1 minus 0.36 is 0.64. I am going to grab me another piece of paper. Hold on. And let's look at 5 and 6 together. Okay. I don't know why I stopped there. That was silly of me. So number 5, we've got blood pressure and platelets. So for number 5, we are going to be looking for an association between them. So the type of graph that we're going to be making if we're looking for an association is going to be a scatter plot. So I'm going to need to first get my data in here, clearing out my lists. So I've got 100, 112. I'm just working across my horizontal one first. And then I'm going to go back, being careful to make sure that they line up with the ones that they're supposed to. 187, 297, 170, 140, 192, 191, 286, 263, and then 193. All right, and then I'm going to go to stat plot, and I want to make a scatter plot. It's already on scatter plot, which is nice. List 1, list 2. Yeah, so that should be good. Zoom stat. Oh, hold on, I gotta be up here, remember? Zoom stat. And that's what my picture looks like. And it looks, oh, let me see. Let me look. It doesn't quite match the answer in the book, so let me see. Maybe I hit something wrong. Sorry. I should have double checked this, but oh well. You get to listen to me ramble. $187, $297, $170, $140, $192, $191, $286, $263. There we go. That looks better. I've got the answer in the book, and I knew I should have something up there. This does not appear to have an association. It doesn't appear to be linear. It doesn't appear to be nonlinear. There doesn't appear to be much of an association here. If we were looking at, say, chapter 10 or something, we could maybe do a test to see if there's any association, but I'm going to save that for later. All right. And then these next ones. Oh, gosh. These ones are looking at, you pay $5 and select 5 different numbers between 1 and 52. So you get 5 numbers between 1 to 52. Okay, and then a 6th number between 1 and 28. Okay, and you get 5 different numbers. Okay, so 3, 4, 5, and then here's your 6th number. So the first number, there are, is that 52? Yeah, there's 52 choices because 0 doesn't count. But then the next time, because you're picking a different number, it's 51, and then 50, 49, 48, and then there are 28 choices for your 6th number that's randomly assigned to you. Okay? So winning requires that your 5 numbers match those drawn in any order. Ooh, any order. So that means we're looking at not a permutation, but just a combination, right? So we're looking at a combination. I'm doing this problem as I'm working with you, so give me a minute. I have to remember stuff too. You probably didn't quite remember these as well. But we've got NCR, right? Where N is the number of different items that are available. So this would be 52. And then C and then R is going to be the number of them that you are picking, which is 5. Okay. So just looking at this, how many possible combinations there are here. So that's under math. Oh, I need 52, math, probability, NCR, and then 5. So that's a lot. 2, 5, 9, 8, 9, 6, 0. Okay, so that's how many possible combinations there are there, but there are also 28 of those because there's that many combinations of those first 5 numbers, but then there's another number assigned to you and it's 1 through 28. So there's 28 more. So that means that there are, oh, hold on. They are breaking, I'm skipping ahead, right? So this is the first 5. And the first problem says, what is the probability of selecting the correct 5 numbers, right? The correct 5? Well, the probability of selecting the correct 5 numbers is going to be 1 over 2, 5, 9, 8, 9, 6, 0. That's part A, right? Part B says, what is the probability of selecting the correct 1 out of 28? Well, there's 28 different possibilities. There's only one way to do it. That one's pretty easy. And then part C, that's the one that I was skipping to, is the probability of getting it all right. So that's going to be 1 over 2, 5, 9, 8, 9, 6, 0 times 1 over 28. And that ends up being 1 over 7, 2, 7, 7, 0, 8, 8, 0. Okay? So these ones, that's where you're looking at those permutations or combinations in this case, because remember, it's a combination. Order doesn't matter. Okay? Sorry, I skipped those on the first one. That was not very good of me. All right, chapter 5. Here we go. All right, so for chapter 5, the first one starts off, once again, looking at data, right? They give you another data set and they say figure it out. In this case, you're looking at the number of moons that each planet has, right? We are right here. We have 1 moon. Mars has 2 moons, so on. A lot of them have more than we do, but that's okay. So you find your mean, median, mode. Remember, mode is the one that occurs the most, which is 0. Find your range, standard deviation. This one I told you to skip the variance, but you could have just squared it and you'd be fine. And then it wants you to use that range rule of thumb to find the upper and lower kind of cutoff points for usual values, right? And so that's your mean plus or minus 2 standard deviations. So your upper cutoff point is 31.6 moons, and then your lower cutoff point is negative 12.4 moons. And we don't have any values in our data set that are significantly high or low. And then it's discrete. You know, a planet cannot have half of a moon. It could have a small moon, but not half of a moon. Okay. The next one, we are looking at, let me turn the page here. This is another kind of lottery thing. And so we're looking at the number of possibilities that we've got. And so if we're picking 3 digits, right, we're picking 3 digits. This one, the order matters. Or no, the order doesn't matter. Never mind. You're just picking 3 digits, but there's repetition allowed. That's the thing. If you can have repetition allowed, so you end up with 10 times 10 times 10 different possibilities. So you've got 1,000 different things. So the probability of getting it right is 1 over 1,000. If you were to buy a lottery ticket every single day for an entire year, then you would have a 0.365 chance of winning because you're going to have that probability every day. And because they are independent events, right? Winning the lottery one day does not affect your ability to win it the next day. Likewise, losing it does not make it more likely for you to win it the next day. So you end up with 0.365. You just multiply it by the number of times that you're doing it. Part C says if you play this game once every day, find the probability of winning exactly once. Well, this is a binomial situation, right? We're dealing with something that has a fixed number of trials, so 365 trials. The probability is always the same for winning. We have a probability of winning and losing. It's definitely a binomial situation, so my n is 365, p is 1 over 1,000, and then I want to win exactly once, so that ends up being 0.2536. And then if we're looking at our, hold on, that's at 999, not 499. There we go. If we're looking at the expected value, right? So you could either win $499, right? Because you spend one, so you get 500 back, so you would win $499, and you have a 1 in 1,000 chance of that happening. Or you could lose $1 because you spend $1, and you've got 999. Hold on, that's weird. My numbers are all out of whack. 498. There we go. So I'm going to have 999 out of 1,000 ways for that to happen. Remember, expected value, you take the value times the probability plus the value times the probability for each different outcome, and then add them all up. And you get a negative 0.498. So you get 0.5 cents that 50 cents or half of $1 that you will lose every time that you play. That's the expected value of that lottery ticket. Okay. Number 3, this one you've got a table. I'm going to put it up here so we can see it real quick. There's this table right here. Grab my papers so we can wobble it everything around. There we go. All right, so for this one, we are looking at challenging calls and comparing that with gender. So they say if one of the 879 challenges is randomly selected, what is the probability that it resulted in an overturned call? So we add these together and we get 231. So you take 231 divided by 879 because we're dealing with the whole total, and we get 0.263. And now if one of the overturned calls is randomly selected, so one of these 231 is randomly selected, what is the probability that the challenge is made by a woman? Well, that's 79. So in this case, it's 79 divided by 231 gives me 0.342 with rounding. So with this one, notice we don't have the entire total there because they just said if one of the overturned calls is selected, right? And then the next, if 2 different challenges are randomly selected without replacement, then find the probability that they both resulted in an overturned call. So the first one is 231 over 879, and then we're drawing another one, but without replacement, right? So that means that now there are 230 of those divided by 278, right? Because there's one less for us to choose from. So we get 0.0688. The next one is, what is the probability it was made by a man or upheld with an overturned call? So that's going to be these 3 things added together, right? Because these are the challenges made by men, and then these are the overturned calls. I don't just want to take this total and add them together, right? Because I would double count this. So I can just add these pieces, or I can take my totals and then subtract that 152. But we end up with 643 out of the 879, so 0.7315. And then the last one is if one of the challenges is randomly selected, find the probability that it was made by a man given that the challenge was upheld with an overturned call. So that means that we are once again limiting our sample space. We don't care about all of these, right? It was upheld with an overturned call. That's that piece of information that was given to us, so we know that this is our sample space. And then the probability that it was made by a man is that 152. So I take 152 divided by 231, and that gives me 0.6580. Okay? So number 4, let me move all my stuff around again. Number 4 is job applicants. So we are looking at, did I not do number 6 here either? Oh my gosh. Okay, well, you can tell I'm in a weird place right now. So number 4, you're looking at The Society for Human Resource Management conducted a survey of 347 human resource professionals and found that 73% of them reported that their companies do criminal background checks. So find the number of respondents that said that they do. And so that's just 73% of that 347. And so that's about 253 people or companies, right? So the sample is the 347 HR professionals, and then the population is all HR professionals because they're looking at, the human resource professionals at different companies, right? So they've only got a sample of 347 of them. 73% is a statistic because it's a number that describes a sample, right? That's 73. It came from a sample, not from a population. So sample, statistic, right? Remember, population goes to parameter. Number 5, we've got a misleading bar graph. If I'm looking at this, it doesn't even really matter what it's about. But as I'm looking at it, this is 6 million. This is 7 million. This looks like it is a huge, huge difference. There's no vertical axis, so it's just 2 chunks, and this one definitely looks smaller than this one, and this one looks like it's almost 3 times as big, right? It's about 3 times the size, when in all reality, the difference is not 3 times as large, right? There's only about a 1 million difference between these, so it definitely should not be that big. So there's definitely some sort of misleading going on there. All right, so for the next one, number 6, we've got probability. Maybe that's why I skipped this one. All right. So we've got, based on the results by a Bradley Corporation poll, assume that 70% of adults always wash their hands after using a public restroom. 70%. I hope that number is not true. I hope that, especially with everything that's going on now, I really hope that number is 98%. But maybe I'm just a little hopeful for humanity. So find the probability that among 8 randomly selected adults, exactly 5 always wash their hands. So this is a binomial situation, right? In this case, n is going to be, so for part A, n is 8, p is 0.7, and then x is going to be 5. We want exactly 5, so I'm going to use binomial, PDF. Remember, P stands for point, right? Binomial PDF of 8, 0.7, and then 5. Let me turn back on calculator. Okay, binomial PDF, 8.75, and I get 0.2541. Part B, find the probability that among 8 randomly selected adults, at least 7, right? So n is still 8, p is still 0.7, but I want at least 7, right? And remember that whenever we're dealing with at least, it's really important to take the time and kind of map out what it is that I want. So if I'm at 7, I'm going to go like 5, 6, 7, 8, right? And so I want at least 7. So these are the numbers that I want. These are the ones that I don't want. So there's 2 different ways that we could do this. We could just find these 2 probabilities and add them up, right? But I'm going to do it in one step just to make it easier for me. I'm actually going to take 1 minus this probability. So this is going to be my x. And so I've got binomial, CDF in this case, right? Cumulative distribution function. It's going to take all of these things and add them up. So 1, 2, 3, 4, 5, and 6. And I've got my n is 8, my probability is 0.7, but then my cutoff point, even though I want at least 7, my cutoff point for the stuff that I don't want is going to be 6. Remember, the cumulative one always goes up to and includes your cutoff point. Okay, so I'm going to do that all at once. So I'm going to go 1 minus, right? I'm just going to do it all in my calculator. 1 minus, I'm going to get to that binomial CDF function, and I've got 8, 0.7, and then 6. And so I've got 0.255, and then rounding to 4 decimal points, that gives me 3. Okay? And then the next one, I'm going to flip it over for this. So for part C, actually I'm not gonna flip it over because then I can't scan it as easily for you guys. And I wanna scan these so that I can upload them for you. So for part C, they are saying for groups of 8 randomly selected adults, find the mean and standard deviation, right? So remember, the mean of these is NP, and then the standard deviation is the square root of N, that's not an N, NPQ, right? Oops, you can't see it because my picture's there. Okay. So my mean is gonna be 8 times 0.7. So my mean, 8 times 0.7, is going to be 5.6 people. And then my standard deviation is the square root of 8 times 0.7 times 0.3. And so my standard deviation is going to be 1.3 people. Okay, then part D, last but not least, for this one. If 8 adults are randomly selected and it is found that exactly one of them washes their hands, is this a significantly low value? So there's a couple of ways that we could do this. We could look at it like we did earlier with that mean minus 2 standard deviations to get what my lower cutoff point is, or we could find a z-score. I'm going to do the mean minus 2 standard deviations. So I'm going to have 5.6 minus 2 times 1.3. And that gives me a cutoff point of 3. So having one person, that is definitely abnormally low. Abnormally low, right? Because 3 would be my cutoff point for the low ones. If I wanted to do it using a z-score, which I could also do, I would take my value. Remember that in this case, my x is 1. That's what I'm concerned with. So remember, a z-score is your observation minus your mean divided by your standard deviation. So I've got 1 minus 5.6 divided by 1.3. And so I get a negative 3.54. That is definitely more than 2 standard deviations away. So it is abnormally low, whichever way we go about it. All right, so the last one for this video is number 6. And I did all of this one. I did the whole thing. You'd be proud of me. I didn't mess this one up. I don't know what I got going on, guys. I'm sorry. All right, so for number 6, for the first one, actually the first 3 really, we're dealing with the New York Knicks and their salaries, right? So we can find our summary statistics, pretty simple. They ask us to find a z-score as well, and so you get a z-score of 2.33 when you do that one, but nothing should be a surprise here. The next one, they want us to make a box plot, right? Excuse me, so they ask us Q1, Q2, and Q3. Remember Q2, that's just our median. Excuse me. That's just our median. There's nothing special going on there, just the median. It just is Q2 is another way to say it because it's the second quartile, right? Here's my min, my first quartile, second quartile, third quartile, or, you know, the median. And then make your box plot, right? It does not appear to be from a normal distribution. If we make a dot plot like it asks us in number 3, it still does not appear to be normal, right? We've got a couple of highly paid players, and then we've got a bunch way down here. So this would be skewed which direction? Skewed, it's pushed from the right, so skewed right. Okay, just a reminder. All right, number 4, we are dealing with the probability that someone has blue eyes is 35%. And then they give us this bar B, right? B is that someone has blue eyes, and so bar B means not B or not blue eyes. So the probability of not B is our complement. That's that 1 minus 0.35, which is 0.65. And then for C, the probability of randomly selecting 3 different people with blue eyes. Oh, sorry, hold on. Yeah. Three different people and all of them have blue eyes, right? So that's going to be a binomial situation. I've got 3 different people. I'm selecting 3. I've got my probability, and I want a total of 3 people to have blue eyes. And so I get, with some rounding going on here, I've got 0.0429 for that probability. And then for part D, this one is another one where I'm breaking it down the same way that I just did in that last problem, right? So I'm looking at the probability if I select 100 people, that at least 40 have blue eyes. So I'm selecting 100, I want at least 40. These are going to be my 40 with blue eyes, right? So 40, 41, 42, this is that part that I want. This is the part that I don't. So I'm going to take 1 minus this probability right here, which is binomial CDF of 100 is my N, 0.35 is P, and then 39 is my cutoff point for the stuff that I don't want, right? And so I get 1.1724, and that's not significantly high. Remember, if it was a high value, then I would be looking at a probability that's going to be less than 5, right? 5% is that cutoff point for significant values. Okay, number 5, we're looking at normal distribution. So we've got foot length, and so we've got a mean of 9.6 and a standard deviation of 0.5. They want to know, find the probability that a randomly selected woman has a foot length less than 10 inches. So I drew my picture. Remember, it's easiest with these, just draw a picture so that you can see what you're looking at. So I've got my area shaded in, and I can find my lower and my upper by using my picture, right? I start here from left to right. My lower is going to be this negative bunch of 9s. It goes up to 10, and then my mean is 9.6, and my standard deviation was 0.5. And I have a probability of 0.7881. And it's always good to make sure that your probability kind of matches my picture, right? This right here is my cutoff point for half. I'm more than half, and that's a little bit more than half. It makes sense. This one, I'm looking at it between 8 and 11. So my picture is not drawn very well to scale. I should have these farther out because my standard deviation is 0.5. Remember, we count over by 0.5s. I just kind of threw an 8 and an 11 there so I can have my lower and my upper bound. But I ended up with normal CDF, lower, upper, same mean and standard deviation, and so I've got 0.9968 for that probability. The next one, so this one, they ask us P95, and P is percentiles. We didn't really do a lot with percentiles, right? So I'm going to do this one for you, and I didn't expect you to do it, right? I had you skipping 5C, but I'm going to do it just because it's the one that uses inverse norm. So when we're dealing with a 95 percentile, we're looking at the cutoff point for the lower 95%. So that means that this area is 0.95. So I can use inverse norm. It asks me for my area to the left. Area is always to the left. And then 9.6 is my mean, 0.5 is my standard deviation. So I get that that cutoff point is 10.4 inches. And then part D, they are randomly selecting 25 people, and they have 25 women, and they want to know if the mean foot length is greater than 9.8, what the probability of that is. They are taking a sample, and we're looking at a sample mean. So we are dealing with the central limit theorem. Remember that central limit theorem, it changes our standard deviation. It doesn't change my mean, right? The mean of all of my x bars is still 9.6, but the mean of my standard deviation of all of my sample means is going to be my standard deviation divided by the square root of my sample size, right? I'm going to write that over here. So it's going to be the standard deviation divided by the square root of n, okay? So that changes my standard deviation. I still draw my picture, and I still work it out the same way, but I just end up with a different probability because my standard deviation is so much smaller. So I have a very small probability, even though 9.8 is not very far away from 9.6, I have a pretty small probability that that would happen, okay? So that's chapter 6. As I said, I'm going to get the other ones out to you probably here later today. I'm still working on them. And let me know if this helps. If you need any more help, let me know. If there's other questions that you want me to go over in more detail, I will. Just shoot me an email or a text and let me know. All right, I miss you guys, and I hope you're doing okay. Adios.